In the autumn of 1845, a man who had grown up in one of the poorest households in London sat alone in his laboratory at the Royal Institution and did something that no scientist had ever done before. He took a piece of glass, held it between the poles of a powerful electromagnet, and shone a beam of polarized light through it. The light changed. Its plane of polarization rotated under the influence of the magnetic field. In that single observation, recorded in his laboratory notebook on the 19th of September, 1845, Michael Faraday had done something that looked, to most of his contemporaries, like a curiosity of experimental physics. A clever trick, an interesting phenomenon to be catalogued and filed. What Faraday understood, in a flash of intuition, that would take the rest of the scientific world another 2 decades to fully comprehend, was that he had just proved something almost impossibly grand. Light, magnetism, and electricity were not separate phenomena. They were expressions of the same underlying reality. They were connected, and if they were connected, then perhaps everything was connected. Perhaps the forces that governed the universe were not a scattered collection of independent powers, but branches of a single, unified tree. He wrote it down in his journal. He told his colleagues. He published it in the Philosophical Transactions of the Royal Society. And then, in a series of letters and lectures over the following years, he began to make predictions. Not the tentative, hedged predictions of a cautious man, but bold, almost reckless statements about what the future of science and human civilization would look like. He predicted that his discovery would lead to technologies that would transform every aspect of human life. He predicted that energy would one day be transmitted without wires across vast distances. He predicted that the forces of nature, properly understood, would give human beings a power over matter that previous generations would have regarded as nothing short of miraculous. And then he made one final prediction, one that he knew, even as he wrote it, might never be verified in his own lifetime. He predicted that all the forces of nature, gravity, electricity, magnetism, the forces that held matter together, were ultimately expressions of a single underlying reality. That one day, a theory would exist that described all of them within a single, unified framework. He was wrong about the timeline. He was right about almost everything else. And that final prediction, the unified theory of all forces, remains to this day the greatest unsolved problem in all of physics. This is the story of Michael Faraday, the blacksmith's son from Newington Butts, who became the greatest experimental scientist in British history, the man who predicted the 20th century from the vantage point of 1845, and the man whose last grandest vision, the one that haunted Einstein for the final 30 years of his life, the one that remains the holy grail of modern theoretical physics, still has not been achieved. If you find stories like this one compelling, the stories that hide behind the official history, the discoveries that shaped everything, the names that should be far more famous than they are, subscribe to this channel now and press the bell so you never miss one. These are the stories that deserve to be told. Michael Faraday was born on the 22nd of September, 1791, in Newington Butts, which is now part of the London borough of Southwark. His father, James Faraday, was a blacksmith who had moved the family south from Yorkshire in search of work. His mother, Margaret, managed the household with the quiet competence of someone who had learned to do a great deal with very little. The family was poor in the specific way that working-class families in late 18th century London were poor. Not destitute, not starving, but always close to the edge, always dependent on the next week's wages, with no buffer between themselves and genuine hardship. Faraday would later say that his early education amounted to very little. Basic reading and writing, a little arithmetic, and the religious instruction of the Sandemanian Church, a small dissenting Christian sect to which the family belonged. The Sandemanians were an unusual group, deeply committed to the literal truth of Scripture, suspicious of worldly ambition, and convinced that the material world was a creation that bore the fingerprints of God in every detail. This last conviction would prove, in unexpected ways, to be one of the most scientifically productive religious beliefs in British history. At the age of 13, Faraday went to work as an errand boy for a bookbinder named George Rebow, who had a shop on Blandford Street in Marylebone. A year later, he was apprenticed to Rebow as a bookbinder's assistant, and it was there, surrounded by books of every description, that his education truly began. He read voraciously. He read what came to hand, and what came to hand was everything: novels, histories, scientific treatises, philosophical texts. He read Jane Marset's Conversations on Chemistry, a popular science book aimed at general audiences, and was immediately and permanently captivated. He began conducting his own crude electrical experiments in the back of the bindery, building a simple battery from coins and brine-soaked paper, connecting wires, watching the small blue spark of electrical discharge. It was a customer at the bookshop, a Mr. Dance, who changed the course of Faraday's life by giving him tickets to attend a series of lectures at the Royal Institution by the chemist Humphrey Davy, the most celebrated scientist in Britain and possibly in the world. Faraday attended 4 lectures in the spring of 1812, took meticulous notes, bound them beautifully, and sent the result to Davy with a letter asking for a position at the Royal Institution. He was 20 years old. Davy, who was a man of considerable vanity and occasional petty jealousy, would later remark, half admiringly, half bitterly, that the greatest discovery of his life was Michael Faraday. He hired him first as a laboratory assistant. He took him on a long tour of Europe, during which Faraday served in the humiliating role of personal valet. He underestimated him in small ways and large ways throughout their association. And yet, despite all of this, Davy gave Faraday access to the finest scientific equipment in England and to the social world of British science. And Faraday, with the focused intensity that would characterize his entire career, made the most of both. By the 1820s, Faraday had already established himself as a first-rate chemist and physicist. He had discovered 2 new compounds of chlorine and carbon. He had produced the first known compounds of carbon and chlorine. He had liquefied chlorine gas. He had invented the steel alloy that would later be recognized as an early form of stainless steel. He had, in 1821, constructed the first electric motor, a device that converted electrical energy into continuous mechanical motion. In a moment of insight so profound that it would take another decade for the scientific community to fully appreciate what he had done. But it was in the decade of the 1830s that Faraday became something more than a very good scientist. He became a visionary. In 1831, working in his laboratory at the Royal Institution, with a ring of iron wound with 2 separate coils of wire, he made the discovery of electromagnetic induction. He showed that a changing magnetic field could generate an electric current, and that an electric current could generate a changing magnetic field. He had discovered the dynamo principle, the fundamental basis of every electric generator and every electric motor ever built. The entire subsequent history of electrical engineering, the power stations that would light the cities of the 20th century, the electric motors that would drive the industries and the transport systems of the modern world, the generators that would, within 100 years of his discovery, make electricity the dominant energy technology of human civilization. All of it descended directly from what Faraday did in his laboratory in the autumn of 1831. He also, in 1833, formulated the laws of electrolysis, the laws governing the relationship between electrical charge and chemical change, which would eventually underpin the electrochemical industries, the electroplating processes, the aluminium smelting techniques, the battery technologies that would define the 20th century. And in 1838, he proposed a theory of electrical action in which the key concept was not the electrical charge itself, but the field, the region of influence surrounding a charged body, the invisible structure of space that mediated the interaction between charges. The concept of the field was Faraday's most revolutionary intellectual contribution. It did not seem so at the time. It seemed, to mathematically inclined physicists like William Thomson and later James Clerk Maxwell, like a useful but somewhat vague physical picture that needed to be turned into proper mathematics before it could be taken seriously. But Faraday's intuition was correct in a way that went deeper than mathematics. The field, the idea that physical interactions were not instantaneous actions at a distance, but were mediated by a continuous, extended physical entity that permeated space, was the key conceptual innovation that would make 20th century physics possible. Quantum field theory, which is the foundation of our understanding of all the fundamental forces of nature, except gravity, is a direct descendant of Faraday's idea. In 1845, the year that concerns us most, Faraday was 53 years old. He had been experiencing episodes of poor health and memory difficulties that would periodically plague him for the rest of his life. Possibly the early symptoms of mercury poisoning from his years of chemical experimentation. Possibly the beginning of a neurological decline. He had taken a year off from research, feeling himself drained and uncertain. He had returned to the Royal Institution in the spring of 1845, but without the consuming intensity of his earlier periods of work. And then, in September of that year, everything changed. The experiment that Faraday performed in September 1845, what he called the magneto-optical effect, and what later scientists would call the Faraday effect, was the culmination of a line of thinking he had been pursuing for years. He had long believed, on grounds that were partly experimental and partly intuitive, that light and electromagnetism were connected. He had tried repeatedly to demonstrate this connection experimentally and had repeatedly failed. The connection, if it existed, was too subtle for his earlier apparatus to detect. In September 1845, with better equipment and a crucial insight about what to look for, he finally found it. When a beam of polarized light passed through a transparent material held in a magnetic field, the plane of polarization rotated. The angle of rotation was proportional to the magnetic field strength. Light was responding to magnetism. Magnetism was affecting light. They were, in some deep sense, the same thing. Faraday's response to this discovery was immediate and characteristic. He did not rest on the result. He did not write it up and submit it and move on to the next experiment. He thought. He thought with the full power of an intellect that had been trained over 30 years of experimental work to see through appearances to the underlying structure of physical reality. And what he saw in the weeks following that September experiment was a vision of the physical world so comprehensive and so radical that it would take science another century and a half to fully explore its implications. He understood that what he had shown was not just a connection between light and magnetism. He understood that he had shown something about the nature of space itself. Light, he reasoned, was not a material substance, not the corpuscular projectiles that Newton had imagined, and not quite the waves in a mechanical medium that most of his contemporaries believed. Light was something else, a disturbance in the electromagnetic field, a ripple in the invisible structure that permeated all of space. And if light was a field disturbance, then all the phenomena of optics, reflection, refraction, interference, diffraction, were phenomena of the electromagnetic field. All of them could, in principle, be explained by a sufficiently complete theory of electromagnetism. This was the insight that Faraday communicated to James Clerk Maxwell in a famous letter in 1857, asking the young Cambridge mathematician to give his physical intuitions mathematical form. Maxwell did so, publishing his equations of electromagnetism in 1865, and those equations, Maxwell's equations, predicted, mathematically, that electromagnetic disturbances would propagate through space at the speed of light. They predicted radio waves, microwaves, X-rays, gamma rays. They predicted the entire electromagnetic spectrum. They predicted wireless communication. They predicted the technologies of the 20th century with a precision that even now remains astonishing. But Faraday had seen further than Maxwell. In a series of lectures and writings in the 1840s and 1850s, Faraday went beyond the connection between light and electromagnetism and speculated about connections that science would not fully explore for another half-century. He speculated about the relationship between gravity and electromagnetism. He speculated that all the forces of nature, the forces that governed the motion of planets, the forces that bound atoms together, the forces that produced the phenomena of electricity and magnetism, were not independent entities, but aspects of a single, underlying unity. He wrote, in 1846, in a lecture at the Royal Institution that was later published as a paper titled Thoughts on Ray Vibrations, he proposed that light was a vibration of the same lines of force that constituted electric and magnetic action. He was not speaking metaphorically. He was making a specific physical claim that the medium of light propagation and the medium of electrical and magnetic action were the same thing, that there was one field, not several, that the universe was simpler than it appeared. He was right, and he was right in a way that pointed directly toward physics' greatest remaining challenge. To understand what Faraday predicted and why his final prediction remains unfulfilled, it helps to trace the path that physics took in the century and a half after his death in 1867. It is a path of extraordinary success and one stubborn, magnificent failure, and it begins with the man who took Faraday's physical intuitions and gave them mathematical form. James Clerk Maxwell was born in Edinburgh in 1831, the same year that Faraday discovered electromagnetic induction. He was everything that Faraday was not, in the superficial sense. Educated at Edinburgh Academy and then at Cambridge, fluent in the mathematical language of differential equations and vector calculus, comfortable in the social world of British academic science. He was also, in the ways that mattered most, everything that Faraday was, possessed of a physical intuition of extraordinary clarity, capable of seeing the world in terms of structures and relations rather than mere particles and forces, and fundamentally committed to the idea that nature was elegant, that the laws governing the universe were not a confused collection of empirical rules, but expressions of a deep and beautiful order. Maxwell's equations, published in their final form in 1865, were the first great unification in the history of physics. They took Faraday's disparate experimental discoveries, the laws of electrostatics, the laws of magnetostatics, the law of electromagnetic induction, the displacement current that Maxwell himself added to make the equations mathematically consistent, and wove them into a single, seamless mathematical structure. From that structure, Maxwell derived the electromagnetic wave equation, and from that equation, he calculated the speed of electromagnetic waves. The number he obtained was, within experimental error, identical to the measured speed of light. It was one of the most dramatic moments in the history of science. Maxwell had not set out to explain light. He had set out to write down the equations governing electricity and magnetism. Light had emerged from those equations as a necessary consequence, as inevitable as the solution of a well-posed mathematical problem. Faraday's intuition that light and electromagnetism were the same thing had been vindicated completely. But the predictions embedded in Maxwell's equations went further than even Maxwell initially appreciated. His equations described waves of electromagnetic energy propagating through empty space. They made no restriction on the frequency of these waves. They allowed waves of any frequency, from the very low to the very high, and they predicted that all these waves would travel at the same speed, the speed of light, regardless of frequency. This was an extraordinary prediction, because in 1865, only one kind of electromagnetic radiation was known: visible light. The rest of the electromagnetic spectrum was entirely unknown, entirely unpredicted by any earlier scientific thinking. Maxwell predicted radio waves. He predicted infrared radiation and ultraviolet radiation as extensions of the visible spectrum. He predicted, implicitly, X-rays, microwaves, and gamma rays, and he predicted, again implicitly but unmistakably, the technologies that would exploit all of these. If electromagnetic waves could propagate through empty space, then electromagnetic waves could carry information through empty space. If information could be encoded in the amplitude and frequency of an electromagnetic wave, it could be transmitted without wires, without any physical connection between sender and receiver, across any distance that the wave's energy could bridge. In 1888, Heinrich Hertz, a German physicist working in Karlsruhe, produced and detected radio waves in his laboratory for the first time. He used a spark gap to generate oscillating electromagnetic fields and a loop of wire as a detector. The waves he produced and detected were exactly what Maxwell's equations predicted. Maxwell had died 9 years earlier, at the age of 48, from abdominal cancer. He never knew that his equations had been confirmed. But Faraday, who had also died 20 years before Hertz's experiment, had been right all along. The connection between light and electromagnetism that he had first demonstrated in September 1845 had led, within 4 decades of his death, to the experimental confirmation of electromagnetic waves, and within another decade, it would lead to the first practical demonstrations of wireless communication. Guglielmo Marconi, the Italian inventor, who is conventionally credited with the invention of radio, understood himself to be applying the physics of Maxwell and Faraday. He filed his first British patent for a wireless telegraphy system in 1896, 51 years after Faraday's September discovery. By 1901, he had transmitted a radio signal across the Atlantic. By 1910, radio was a practical communication technology used by ships at sea. By 1920, the first regular public radio broadcasts had begun. By 1940, within a century of Faraday's 1845 experiment, radio was a mass medium reaching into the homes of hundreds of millions of people. The speed of this development was, in historical terms, extraordinary. Faraday had made a discovery in a laboratory in 1845. That discovery, processed through Maxwell's equations and Hertz's experiments and Marconi's engineering, had become a global communication technology within 50 years. No previous scientific discovery had ever translated into practical technology so quickly or with such comprehensive social consequences. And the consequences did not stop with radio. Television, the transmission of moving images through the electromagnetic spectrum, followed within decades of radio. The first public television broadcasts in Britain began in 1936, courtesy of the BBC, 91 years after Faraday's magneto-optical experiment. Radar, the technology that would prove decisive in the Battle of Britain in 1940, exploited the same electromagnetic wave physics. Microwave ovens, mobile phones, satellite communications, wireless internet, GPS navigation, all of them are direct technological descendants of the September experiment that Faraday performed in his Royal Institution laboratory in 1845. But Faraday's predictions were not limited to the technologies of electromagnetic radiation. He had also, in his 1831 discovery of electromagnetic induction, laid the theoretical foundation for the electrical power industry that would come to define the 20th century. The basic principle of every electric generator ever built is Faraday's law of electromagnetic induction. A changing magnetic field induces an electric current in a conducting wire. This is true whether the changing magnetic field is produced by moving a permanent magnet near a coil of wire, or by passing a current through an electromagnet whose field varies over time, or by rotating a coil of wire in a static magnetic field. The geometry changes, the scale changes, the efficiency changes, but the underlying physics is always Faraday's. The first practical electric generators were built in the 1870s. By the 1880s, Thomas Edison in New York and Sebastian de Ferranti in London were constructing the first commercial electric power distribution systems. Edison's Pearl Street Station in Manhattan, which began operation in September 1882, supplied direct current electricity to a small district of Lower Manhattan from a central generating station. Ferranti's Deptford Power Station in London, which came online in 1891, supplied alternating current at much higher voltages, allowing it to distribute electricity over a much larger area. The battle between direct and alternating current systems, the so-called War of Currents, fought between Edison and Westinghouse and Tesla in the United States, was resolved in favor of alternating current by the early 1890s. By 1900, electric street lighting had transformed the nighttime appearance of every major city in the industrialized world. By 1920, electricity was reaching into the homes of the urban middle classes throughout Britain and America, powering electric lights, electric fans, and the first domestic electrical appliances. By 1940, electrification was nearly universal in British towns and cities, and rural electrification schemes were bringing power to the countryside. By 1950, the electrical power system had become so integrated into the fabric of daily life that its absence, even briefly, constituted a social emergency. None of this would have been possible without Faraday's 1831 discovery of electromagnetic induction. He could not have anticipated the specific technologies, the three-phase alternating current system, the steam turbine, the hydroelectric dam, that the electrical industry would eventually employ, but he had understood the principle, and he had understood its implications. In 1831, immediately after his discovery, he showed a model of his induction coil to a government official who asked what it was good for. Faraday's reply, sometimes quoted as a response to a similar question by Gladstone, though the attribution is disputed, was characteristic. What is the use of a newborn child? He meant that the discovery was a beginning, not an end, and that its ultimate uses could not be foreseen from the vantage point of the moment of discovery. He was right in a way that exceeded even his own imagination. The electrical power industry, built on Faraday's discoveries, did not merely transform the material conditions of human life. It transformed the structure of human civilization. It made possible the large-scale industrial production that characterized the 20th century. It made possible the information technologies, radio, television, the internet, that transformed communication and culture. It made possible the medical technologies, diagnostic imaging, life support systems, surgical equipment, that transformed healthcare. It made possible the agricultural technologies, electric irrigation pumps, refrigerated food storage and transport, electrically powered processing machinery, that transformed food production and distribution. It is not an exaggeration to say that the 20th century, in its most characteristic features, was a century built on Michael Faraday's discoveries. The third major strand of Faraday's predictions concerned the nature of matter itself. In the 1840s and 1850s, long before the development of quantum mechanics and the discovery of the atom's internal structure, Faraday made observations and proposed ideas that pointed unmistakably toward the physics of the 20th century. His discovery of the laws of electrolysis in 1833 had already revealed something important about the relationship between electricity and matter. The laws stated that the amount of chemical change produced by an electric current was proportional to the quantity of electricity passed, and that different elements required different quantities of electricity to deposit equal chemical equivalents. This implied, Faraday argued, that electricity was not a continuous fluid, but came in discrete quantities. That there was, as he put it, an atomicity to electrical charge. He was describing, in the vocabulary of 1833, what would later be identified as the electron, the elementary unit of electrical charge, the discovery of which, in 1897, is usually attributed to J. Thomson. Thomson himself acknowledged that Faraday's electrolysis laws had pointed toward the electron's existence. In discovering the electron and receiving the Nobel Prize for it, Thomson was in a real sense completing a theoretical journey that Faraday had begun 60 years earlier. Faraday had predicted the atomicity of electric charge. Thomson confirmed it. The age of the electron, of electronic technology, of transistors, of computers, of every device that processes information electrically, began with Thomson's confirmation of Faraday's prediction. But Faraday's speculations about the nature of matter went further than the electron. In a remarkable paper published in 1844 and in subsequent lectures and writings, he proposed an idea that was at the time so radical that most of his contemporaries simply did not know what to do with it. He proposed that atoms, which by 1844 were generally accepted by chemists as real physical entities following the work of John Dalton, were not small hard spheres of matter, as Dalton and most other chemists imagined them. They were, Faraday proposed, centers of force, points around which fields of force extended throughout space. Matter, in Faraday's vision, was not stuff surrounded by fields. Matter was fields. The distinction between matter and the forces that acted between pieces of matter was not a fundamental distinction. Matter was force, concentrated. This idea, which Faraday called the theory of point atoms, was regarded by his contemporaries as a speculative curiosity, interesting perhaps as a metaphysical position, but not susceptible to experimental testing. It was dismissed, gently but firmly, by the mainstream of British physics and chemistry. It was not wrong. The 20th century's physics of matter, quantum mechanics, quantum field theory, the standard model of particle physics, converged on precisely the picture that Faraday had sketched. Particles, in modern physics, are not little hard spheres. They are excitations of quantum fields, ripples in the fabric of space-time, concentrated disturbances in the underlying field structure of reality. The electron is not a small ball of matter. It is an excitation of the electron field that pervades all of space. The proton and neutron are not hard spheres but complex structures built from quarks, which are themselves excitations of quark fields. Matter is field, force is field. The distinction between the two has dissolved in modern physics almost entirely. Faraday did not have the mathematics to say any of this precisely. He did not have quantum mechanics or special relativity or the concept of gauge invariance that underlies the standard model. What he had was physical intuition of such clarity and depth that it pierced through the inadequate conceptual vocabulary of his time and pointed, however imprecisely, at the structure that 20th century physics would eventually reveal. The story of how Faraday's physical intuitions were given mathematical form is one of the great narratives of intellectual history, and it runs directly through the figure of James Clerk Maxwell. Maxwell's equations did not merely unify electricity and magnetism and light. They introduced the concept of the electromagnetic field as a fundamental physical entity. Not a shorthand for calculating forces between charges, but a real physical thing that existed independently, that could propagate through empty space, that carried energy and momentum. This was Faraday's field concept given mathematical form, and it was the conceptual revolution that made 20th century physics possible. The physicist who took the next step, who built on Maxwell's field concept to create the framework within which all of 20th century physics would operate, was Albert Einstein. And the story of Einstein and Faraday is one of the most intellectually moving in the history of science, because it is a story about a great scientist attempting to complete a vision that another great scientist had begun a century earlier, and failing, nobly, magnificently, productively failing, in a way that illuminated how much remained to be done. Einstein came to physics as a young man through Maxwell's equations. It was the apparent inconsistency between Maxwell's electromagnetism and Newtonian mechanics, specifically the question of what the speed of light was relative to, that led him to special relativity in 1905. And it was the insight of special relativity that space and time were not independent, but formed a single, four-dimensional continuum, that led him, a decade later, to general relativity, the theory of gravity as curvature of space-time. General relativity, published in 1915, was the second great unification in the history of physics. It unified gravity and geometry. It showed that what Newton had described as a force, the gravitational attraction between massive bodies, was actually the effect of the curvature of space-time caused by the presence of matter and energy. Gravity was not a force pulling objects together. It was the curvature of the arena in which they moved, and objects moving freely in curved space-time followed paths, geodesics, that looked from the perspective of an observer who thought space-time was flat, like the paths of objects subject to gravitational force. This was a profound conceptual leap. It was also, in a deep sense, the confirmation of Faraday's intuition that matter and space were not independent. In Faraday's vision, matter was concentrated field, and field pervaded space. In Einstein's general relativity, matter and energy curved space-time, and the curvature of space-time determined the motion of matter and energy. The two pictures, Faraday's and Einstein's, were different in their details, but deeply consonant in their underlying thrust. Both saw the universe as a unified, self-interacting whole, in which the distinction between matter and the space through which it moved was more apparent than real. And then Einstein began to pursue Faraday's final prediction. He had, by 1920, two great field theories at his disposal. He had Maxwell's electromagnetism, now reformulated in the language of special relativity, which had shown that electric and magnetic fields were not independent entities, but different aspects of a single electromagnetic field, their appearance depending on the relative motion of observer and source. And he had general relativity, his own theory of gravity, as space-time curvature. Both theories were field theories. Both described fundamental forces in terms of fields that pervaded all of space. Both were extraordinarily successful. Maxwell's equations predicted the electromagnetic spectrum and had been confirmed to extraordinary precision by experiment, and general relativity had been confirmed by the observation of the bending of starlight around the Sun during the 1919 solar eclipse, an observation that had made Einstein, overnight, the most famous scientist in the world. What Faraday had predicted, and what Einstein now set out to demonstrate, was that these two theories were not separate, that electromagnetism and gravity were not independent forces, but aspects of a single, more fundamental theory. That there was, as Faraday had written in 1849, some possible and even likely connection between gravity and electricity. Einstein spent the last 30 years of his life, from roughly 1925 until his death in 1955, attempting to construct a unified field theory, a single mathematical framework that would describe both electromagnetism and gravity within a single coherent structure. He tried many approaches. He explored the geometry of higher dimensional spacetimes. He investigated the mathematics of spinors and torsion. He corresponded with mathematicians and physicists across Europe and America, following every promising lead, abandoning approaches that failed, returning to old ideas with fresh eyes. He produced a succession of papers on unified field theory, each announcing a promising new approach, each eventually revealing its own inadequacies. He failed, not for lack of intelligence or effort, but because the problem was harder than he imagined. Harder, in fact, than the conceptual framework available to physics in the first half of the 20th century could accommodate. The reason he failed is now understood, and it is deeply instructive. Between 1920 and 1940, while Einstein was pursuing his unified field theory, the rest of physics was undergoing a revolution that Einstein himself had helped initiate, but which he never fully accepted. Quantum mechanics, the theory of the behavior of matter and energy at atomic and subatomic scales, was developed during the 1920s, primarily by Heisenberg, Schrödinger, Born, Dirac, and Pauli. It was a theory utterly unlike anything that had come before. It described physical quantities not as definite values, but as probability distributions. It placed fundamental limits on what could be simultaneously known about a physical system. It introduced the concept of the wave function, a mathematical object that encoded the full quantum state of a system and evolved in time according to a linear equation. Einstein found quantum mechanics profoundly unsatisfying. It was not that he denied its predictive power. He acknowledged, reluctantly, that it worked. But it seemed to him to be an incomplete theory, a collection of calculational rules that produce correct answers without revealing the underlying physical reality. The famous remark, "God does not play dice," expressed his conviction that the probabilistic nature of quantum mechanics was not a feature of nature, but a symptom of our ignorance. He believed that quantum mechanics was a good approximation to a deeper, deterministic theory that would eventually be discovered. He was probably wrong about this, but his dissatisfaction with quantum mechanics had a practical consequence for his unified field theory program. He tried to construct a unified field theory on the basis of classical field theory, the mathematical framework of Maxwell and general relativity, without incorporating quantum mechanics. He believed that if he could find the right classical field theory, the quantum behavior of matter would emerge from it naturally. He was pursuing a version of Faraday's vision, a single, unified field describing all of nature, but in a framework that the rest of physics had moved beyond. The rest of physics was moving toward a different kind of unification. Not the unification of classical fields, but the unification of quantum mechanics with the field concept. The result was quantum field theory, the framework in which every particle is an excitation of a quantum field, and the interactions between particles are mediated by the exchange of other particles. In quantum field theory, the electromagnetic force is mediated by the exchange of photons, particles of light, and the theory of the electromagnetic force within this framework, called quantum electrodynamics, or QED, was developed by Feynman, Schwinger, and Tominaga in the late 1940s and early 1950s. QED was, when it was completed, the most precisely tested theory in the history of science. Its predictions agreed with experiment to better than 1 part in a billion, a precision comparable to measuring the distance from London to New York to within the thickness of a human hair. It was a triumph of theoretical physics on a scale that had never been achieved before, and it was built at its foundation on Faraday's insight that the electromagnetic force was mediated by a field, and that the quantization of that field produced particles, photons, that carried the force. The success of QED prompted physicists to try the same approach for the other known forces. By the 1940s, 2 more fundamental forces had been identified beyond gravity and electromagnetism: the strong nuclear force, which bound protons and neutrons together in atomic nuclei, and the weak nuclear force, which was responsible for radioactive beta decay. Could these forces also be described by quantum field theories? Could those theories be unified with QED? The answer, it turned out, was yes, partially. In the 1960s and early 1970s, Sheldon Glashow, Abdus Salam, and Steven Weinberg developed the electroweak theory, a quantum field theory that unified electromagnetism and the weak nuclear force within a single mathematical framework. At low energies, the energies accessible to everyday experience, the electromagnetic and weak forces appeared utterly different. Electromagnetism was a long-range force mediated by massless photons, while the weak force was a short-range force mediated by massive particles called the W and Z bosons. But at very high energies, the energies that had prevailed in the early universe, fractions of a second after the Big Bang, the 2 forces merged into a single, electroweak force. The W and Z bosons, Glashow, Salam, and Weinberg showed, acquired their mass through a mechanism involving a new field, the Higgs field, whose quantum excitation was the Higgs boson. Glashow, Salam, and Weinberg received the Nobel Prize in 1979. The W and Z bosons were discovered experimentally at CERN in 1983, confirming the electroweak theory. The Higgs boson was discovered at CERN in 2012, completing the confirmation of the mechanism that gave mass to the W and Z bosons. The electroweak theory was vindicated in its entirety. It was the 3rd great unification in the history of physics, and it extended Faraday's program, the program of unifying the apparently separate forces of nature, 1 step further. Combined with the quantum field theory of the strong nuclear force, quantum chromodynamics, or QCD, developed through the 1970s, the electroweak theory forms the core of what physicists call the Standard Model of particle physics. The Standard Model describes 3 of the 4 known fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, within a single quantum field theoretical framework. It describes 17 fundamental particles, 6 quarks, 6 leptons, 4 gauge bosons that carry the forces, and the Higgs boson. And it has been tested to extraordinary precision across an enormous range of experimental conditions, from the low energies of everyday physics to the high energies produced in particle accelerators like the Large Hadron Collider at CERN. At every test, it has passed. It is the most successful scientific theory in history. It is also, as its name suggests, a model rather than a final theory. It is successful not because it is obviously correct, but because it is the best framework we have found that is consistent with all available experimental evidence. And it has one enormous glaring omission: gravity. The Standard Model does not include gravity. General relativity, Einstein's theory of gravity as spacetime curvature, is not incorporated into the Standard Model and cannot be incorporated into it without fundamental modifications to one or both theories. The mathematics of general relativity and the mathematics of quantum field theory are deeply incompatible. When physicists attempt to apply quantum field theory methods to gravity, to construct a quantum theory of gravity analogous to QED or QCD, they encounter mathematical infinities that cannot be removed by the standard techniques, called renormalization, that make QED and QCD tractable. Gravity, in the language of quantum field theory, is not renormalizable. This is not a minor technical problem. It is a sign of a deep conceptual incompatibility between the two greatest theories in physics. General relativity describes gravity as a feature of the geometry of space-time, a smooth, continuous, classical geometric structure. Quantum field theory describes the world as fundamentally granular, probabilistic, and non-deterministic at small scales. These two descriptions of reality cannot both be correct at the smallest scales. The Planck scale, about 10 to the power of minus 35 meters, where both gravity and quantum effects are equally important. At the Planck scale, the smooth space-time of general relativity must break down, and something else, some deeper theory that incorporates both gravity and quantum mechanics, must take over. What that deeper theory is, nobody knows. This is the great unsolved problem of fundamental physics, the problem that has occupied the best minds in theoretical physics for the past 60 years and remains, as of today, unsolved. It is, in its deepest formulation, the problem that Faraday identified in 1849 when he wrote in his notebook that he was seeking some likely connection between gravity and electricity. He did not have the vocabulary to state the problem precisely. He did not know about quantum mechanics, or the Standard Model, or the Planck scale, but he understood, with the clarity of vision that characterized his entire scientific life, that gravity and the other forces of nature must ultimately be expressions of a single underlying reality, and that, until a theory existed that unified them, the picture of the universe that physics offered was necessarily incomplete. He was right, and the problem he identified is still open. The history of attempts to solve it is a story of tremendous ingenuity and repeated frustration, and it is worth tracing in some detail, because it illuminates both how far physics has come since Faraday's time and how much further it still has to go. The first serious attempt to unify gravity and electromagnetism, beyond Einstein's long and ultimately unsuccessful program, was made by Theodore Kaluza in 1919 and extended by Oscar Klein in 1926. Kaluza noticed that if you extended general relativity from 4 dimensions of space-time to 5, adding one extra spatial dimension, the equations naturally decomposed into the equations of general relativity in 4 dimensions plus the equations of electromagnetism. Gravity and electromagnetism could be unified, Kaluza showed, if space-time had one more dimension than we can perceive. Klein proposed that this extra dimension was not infinite, but curled up into a tiny circle, so small that we cannot detect it directly. The Kaluza-Klein theory was beautiful and was admired by Einstein, who spent several years trying to extend it. But it had problems. It predicted the existence of particles that were not observed. It could not be made compatible with quantum mechanics in a straightforward way. It offered no explanation for the strong and weak nuclear forces, which had not yet been identified as forces of a fundamentally different character from electromagnetism. It was eventually abandoned, though the idea of extra dimensions, compactified spatial dimensions too small to detect directly, would return in a much more elaborate form decades later. Throughout the 1950s, 1960s, and 1970s, as the Standard Model was being developed, the problem of quantum gravity was set aside, not because physicists had lost interest in it, but because the energies required to probe the Planck scale were so far beyond the reach of any conceivable accelerator that direct experimental tests seemed impossible, and because the theoretical difficulties were severe enough that progress required new conceptual tools that did not yet exist. The focus of fundamental physics during these decades was on the Standard Model, and the remarkable success of that program, culminating in the prediction and discovery of the W, Z, and Higgs bosons, seemed to justify the deferral of the gravity problem. But in the late 1960s and early 1970s, a new set of theoretical ideas began to emerge that would eventually coalesce into the dominant framework for the unification of gravity with the other forces. These ideas were originally developed in the context of the strong nuclear force, not gravity. In 1968, Gabriele Veneziano, an Italian physicist working at CERN, discovered a mathematical formula, the Euler beta function, that successfully described the scattering of strongly interacting particles. This formula was eventually interpreted as describing particles not as points, but as tiny, one-dimensional objects, strings. The idea of string theory, that the fundamental constituents of nature are not zero-dimensional point particles but one-dimensional vibrating strings, was initially developed as a theory of the strong force. But in 1974, John Schwarz and Joel Shirk made a crucial observation. The string spectrum contained a massless spin 2 particle, which had exactly the properties that the hypothetical quantum of gravity, the graviton, was expected to have. String theory, they argued, was not a theory of the strong force. It was a theory of gravity, and because it naturally incorporated the other forces as well, it might be the theory of everything, the long-sought unified theory of all the fundamental forces of nature, the theory that Faraday had predicted and Einstein had spent 30 years failing to find. The subsequent history of string theory is one of the most intellectually dramatic stories in the history of science. In 1984, Michael Green and John Schwarz demonstrated that string theory was free of a class of mathematical inconsistencies, anomalies that had seemed to doom it. This result, which became known as the first superstring revolution, touched off an explosion of research activity. Within a year, the physics community had identified 5 distinct string theories, each potentially consistent, each offering a different detailed picture of the universe. In the early 1990s, it became apparent that these 5 string theories were not genuinely distinct, but were different limiting cases of a single, 11-dimensional theory called M theory, whose full formulation remained and remains unknown. The second superstring revolution of the mid-1990s, initiated primarily by Edward Witten, established this web of dualities connecting the different string theories and suggested that M theory was the unique, consistent quantum theory that unified all the forces of nature, including gravity. Finding the full formulation of M theory became the central problem of theoretical physics. It remains unsolved. After more than 50 years of development, string theory has not produced a single verified experimental prediction. This is not because the theory is obviously wrong. It is extraordinarily difficult to extract predictions from string theory that are testable at the energies accessible to current or foreseeable accelerators. Because the characteristic energy scale of string theory is the Planck scale, which is approximately 16 orders of magnitude above the energies probed by the Large Hadron Collider. String theory might be correct, it might be wrong. Currently, there is no experimental way to tell. This is not the only approach to quantum gravity. Loop quantum gravity, developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin in the 1980s and 1990s, takes a different starting point. It attempts to quantize general relativity directly, treating space-time itself as the quantum system. In loop quantum gravity, space-time is not continuous but discrete at the Planck scale. It is woven from a network of quantum geometric structures called spin networks, whose excitations describe the quantum states of space and time. Like string theory, loop quantum gravity has not yet produced verified experimental predictions, and the relationship between the two approaches remains a matter of active research and debate. Other approaches include causal dynamical triangulations, asymptotic safety, and various versions of non-commutative geometry. All are attempts to find the same thing, a theory that reduces to general relativity at large scales and to quantum field theory at small scales, that is mathematically consistent, and that makes predictions that can be tested experimentally. None has yet succeeded in all 3 requirements simultaneously. The situation in fundamental physics at the beginning of the 21st century is therefore exactly what Faraday's prediction implies. We have an extraordinarily successful description of 3 of the 4 fundamental forces, and no successful unification of those forces with the 4th. We have 2 theories, the Standard Model and general relativity, that are each spectacularly successful within their respective domains and utterly incompatible with each other at the mathematical level. We know that both theories are, at some level, approximations to a deeper truth, because they cannot both be correct at the Planck scale, but we do not know what that deeper truth is. Faraday wrote in 1849 that gravity and electricity must be connected. He was right that they are connected at the deepest level by being aspects of the single, unified physical reality that constitutes the universe. He was right that a theory that unified them must exist. He was right that finding that theory was the most important outstanding problem in physics. He was wrong only in one respect. He could not have imagined how hard the problem would turn out to be. The story of why the problem is so hard is itself a story that illuminates the nature of scientific progress, and it is worth telling in some detail. The incompatibility of general relativity and quantum mechanics is not merely a technical problem, a question of getting the mathematics right. It reflects a deep conceptual tension between the two theories' most basic assumptions. General relativity assumes that space-time is a smooth, continuous geometric structure. Quantum mechanics, or more precisely, quantum field theory, assumes that the physical world is granular and probabilistic at small scales. These two assumptions cannot both be correct. At small enough scales, the Planck scale, the smooth geometry of space-time must break down into something else. What that something else is, and how to describe it mathematically, is the central problem. The difficulty is compounded by the fact that we have no direct experimental access to the Planck scale. The Large Hadron Collider, the most powerful particle accelerator ever built, probes energies of about 10 TeV, 10 trillion electron volts. The Planck scale corresponds to energies of about 10 to the power of 28 eV, about 10 quadrillion times higher than the LHC can reach. No conceivable accelerator built with current or foreseeable technology could probe the Planck scale directly. This means that the theoretical ideas competing to describe quantum gravity cannot, at present, be tested against experiment in the direct way that QED and the electroweak theory were tested. This experimental inaccessibility is unprecedented in the history of physics. When Faraday made his predictions, the technologies to test them, the apparatus to detect radio waves, the equipment to generate electrical power at scale, the particle accelerators to probe the structure of matter, lay decades in the future, but they were in principle within reach. The experiments that confirmed Maxwell's equations, that discovered the electron, that revealed the nuclear structure of the atom, that detected the W and Z bosons, all of these were possible to perform with the technology available at the time, or with technology whose development was a matter of engineering rather than fundamental conceptual breakthrough. The experiments needed to test theories of quantum gravity are not merely technologically challenging. They may be, in principle, beyond the reach of any experimental apparatus that could be built within the physical universe. This creates a philosophical problem for fundamental physics that has no precedent in its history. Physics has always been an empirical science. Its theories have always been tested against experiment, and the criterion for accepting or rejecting a theory has always been whether it agrees with experiment. If the predictions of a theory of quantum gravity cannot be tested against experiment, if the characteristic predictions of string theory or loop quantum gravity or any other approach are necessarily confined to energy scales that are forever beyond experimental reach, then what becomes of the scientific method as a guide to choosing between theoretical frameworks? This problem is not unique to quantum gravity. It applies to any theoretical framework that makes predictions only at energy scales or length scales that are experimentally inaccessible. It has generated a fierce and unresolved debate within the theoretical physics community about the epistemological standards appropriate to fundamental physics, about whether a theory can be accepted as scientific if it makes no testable predictions, about whether theoretical beauty and mathematical consistency are reliable guides to physical truth in the absence of experimental confirmation. Faraday, who conducted his science with a meticulous attention to experimental verification and a deep suspicion of theoretical speculation, that went beyond what experiments could test. Would have found this situation troubling. He was above all an experimentalist. He believed in the primacy of observation and measurement. He distrusted mathematics that ran ahead of experiment. He would, I think, have been deeply uncomfortable with a situation in which the central problem of physics, the unification of gravity with the other forces, had generated a rich mathematical superstructure of theoretical ideas that floated, unanchored, above the world of experimental fact. And yet, it was Faraday himself who, by identifying the unification of all forces as the central outstanding problem of physics, pointed physics toward the very situation in which it now finds itself. He could not have anticipated the specific difficulties. He could not have known that the incompatibility of general relativity and quantum mechanics would prove so deep and so resistant to standard techniques. He could not have known that the energies required to probe the relevant physics would exceed, by 16 orders of magnitude, anything that experimental physics could access. But he pointed. He pointed at the problem, clearly and specifically, in 1849. And physics has been following the direction of his pointing ever since. Whether the unification of gravity with the other forces will be achieved in the 21st century, or the 22nd, or some century further still, is a question that no one can answer. The history of physics offers grounds for both optimism and caution. The optimism comes from the record of success. Every major unification that seemed, at the time it was achieved, to be extraordinarily difficult, turned out to be achievable. Maxwell's unification of electricity and magnetism and light, Einstein's unification of gravity and geometry, the electroweak unification of Glashow, Salam, and Weinberg. Each of these required conceptual innovations that could not have been anticipated from the state of physics at the time. Each required not just new mathematics, but new ways of thinking about the physical world. If the pattern holds, the unification of gravity with the standard model will require a similarly radical conceptual breakthrough, a breakthrough that, by definition, cannot be anticipated from the current state of physics. The caution comes from the scale of the difficulty and the current impasse. Physics has been trying to unify gravity with quantum mechanics for more than 60 years, and despite extraordinary ingenuity and effort, the problem remains unsolved. The experimental inaccessibility of the Planck scale removes the most powerful tool that physics has historically used to break out of theoretical impasses. The unexpected experimental result that forces theorists to abandon their assumptions and think in new ways. Without such results, theoretical physics must rely on internal consistency, mathematical beauty, and the slow accumulation of theoretical insight. Progress is possible by this route, but it is slow and uncertain. The Large Hadron Collider, which began operations in 2008 and has been running at its design energy since 2015, has produced an enormous amount of experimental data, but its most significant result for fundamental physics, the discovery of the Higgs boson in 2012, was expected by the Standard Model. The LHC has found no evidence of physics beyond the Standard Model, no supersymmetric particles, no extra dimensions, no unexpected new forces or fields. This is simultaneously a confirmation of the Standard Model's extraordinary predictive power and a profound disappointment for theoretical physicists hoping for experimental guidance toward a theory beyond the Standard Model. Plans for successor accelerators to the LHC, including the Future Circular Collider at CERN, which would be nearly 4 times larger than the LHC, and various proposed linear colliders in Asia and Europe, are in various stages of planning and design. These machines, if built, would probe energies perhaps an order of magnitude above the LHC, potentially revealing physics beyond the Standard Model that the LHC has missed. But they would still be many orders of magnitude below the Planck scale, and their results, while potentially transformative, cannot be counted upon to resolve the quantum gravity problem directly. Other experimental approaches offer some hope. Gravitational wave astronomy. The detection of gravitational waves by observatories like LIGO and Virgo, and, in the future, the space-based LISA mission, opens a new observational window on the universe that may eventually provide data relevant to quantum gravity. The detection of gravitational waves from the merger of black holes and neutron stars has already confirmed general relativity in strong field, high-velocity regimes that were previously inaccessible. Future observations of gravitational waves from the very early universe, if such waves can be detected, might carry imprints of Planck-scale physics that would provide the first experimental constraints on theories of quantum gravity. Observations of the cosmic microwave background, the afterglow of the Big Bang, have already provided information about the earliest moments of the universe, and future CMB experiments may detect signatures of the quantum gravity era. High-energy cosmic ray astronomy, precision tests of the equivalence principle, and searches for violations of Lorentz invariance at very high energies. All are experimental programs that might, in principle, provide data relevant to quantum gravity. None of them has yet done so, but the field of experimental evidence is expanding, slowly, in directions that might eventually illuminate the Planck scale. The theoretical landscape has also evolved in ways that offer some grounds for optimism. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, established a profound and unexpected connection between certain theories of quantum gravity, specifically string theory in anti-d space, and certain quantum field theories without gravity, conformal field theories, in one fewer dimension. This duality, which has generated tens of thousands of research papers since its discovery, has allowed physicists to use the tools of quantum field theory to study problems in quantum gravity, and vice versa. It has provided a precise, mathematical context in which the conceptual tensions between general relativity and quantum mechanics can be explored, not in the real universe, which is not anti-de Sitter space, but in a class of model universes where both theories are simultaneously applicable. The ADS-CFT correspondence has not solved the quantum gravity problem, but it has provided a new set of tools and a new set of insights. It has shown that the quantum gravity problem is connected in unexpected ways to problems in condensed matter physics, quantum information theory, and the theory of black holes. It has revealed that the geometry of space-time can emerge from quantum entanglement, that the connectivity of space is related to the entanglement structure of the quantum state of matter. This insight, which has been developed over the past decade into a research program called ER-EPR, after a proposal by Maldacena and Susskind that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen pairs, entangled particles are different descriptions of the same physical phenomenon, suggest that the quantum gravity problem and the foundations of quantum mechanics are more deeply connected than anyone had previously suspected. All of this, the ADS-CFT correspondence, the ER-EPR proposal, the connections between quantum gravity and quantum information, points toward a picture in which space-time itself is an emergent phenomenon, something that arises from a more fundamental quantum structure, rather than being a fundamental ingredient of reality. This is a radical idea, and its implications are not yet fully understood, but it resonates, in a deep and perhaps not coincidental way, with Faraday's intuition that matter and space were not independent, that the universe was a single, unified field, and that the apparent separateness of its different aspects was an illusion arising from our limited perspective. The philosophical implications of Faraday's vision, and of the unfinished project that his vision initiated, extend beyond the technical details of theoretical physics. They bear on some of the deepest questions that human beings have asked about the nature of reality, and they have a bearing on questions that are not, or not merely, scientific. Faraday was a deeply religious man, and his scientific vision was inseparable from his religious beliefs. The Sandemanian conviction that the material world was a creation that bore the fingerprints of God in every detail expressed itself, in his science, as a conviction that the physical universe was fundamentally orderly, unified, and comprehensible. He believed that the apparent complexity and variety of natural phenomena concealed an underlying simplicity, and that the task of science was to reveal that simplicity. This was not, for Faraday, merely a methodological assumption, a bet about how science should proceed. It was a theological conviction, as deep and as certain as any article of faith. The universe was one because God was one. His scientific discoveries confirmed this conviction at every turn, every unification. The unification of electricity and magnetism, the unification of magnetism and light, the discovery that the laws of electrolysis implied the quantization of charge, seemed to him a revelation of the underlying unity of nature. And his final prediction, that gravity and the electromagnetic force must be unified, was, in part, an expression of this theological conviction. Not the conclusion of a logical argument, but the articulation of a faith. The faith that the universe, at its deepest level, was simple. Modern physics has not confirmed this faith. It has revealed, at every level it has reached, that nature is more unified than it appeared at the level above. Maxwell. Unified electricity, magnetism, and light. The electroweak theory unified the electromagnetic and weak forces. The Standard Model unified the electroweak theory and the strong force within a single mathematical framework. Each step reduced the number of apparently independent fundamental entities. Each step increased the apparent simplicity of the underlying structure. The trajectory of physics over the past 150 years has been exactly what Faraday's faith would have predicted: a progressive unification, a progressive simplification, a progressive revelation of the underlying order. But each step has also revealed new complexity. Maxwell's electromagnetism was simpler than the patchwork of empirical laws it replaced, but the mathematics of field theory is far more complex than the mathematics of point mechanics. The Standard Model is simpler, in principle, than the collection of separate force laws it unifies, but its mathematical structure, involving gauge symmetries, spontaneous symmetry breaking, the Higgs mechanism, and the complex phenomenology of the strong interaction, is formidably intricate. General relativity in its conceptual framework is simpler than Newtonian gravity plus electromagnetism, but its mathematical machinery, Riemannian geometry, tensor calculus, the Einstein field equations, is among the most demanding in all of physics. The unification of gravity with quantum mechanics, if it is ever achieved, will almost certainly follow the same pattern. It will be simpler in principle, a single, consistent mathematical framework instead of two incompatible ones, but more complex in its mathematical machinery than anything that came before. It will be a theory that, in the limit of low energies and large distances, reduces to both general relativity and the Standard Model, just as general relativity reduces to Newtonian gravity in the limit of weak fields and low velocities, and just as the Standard Model reduces to classical electromagnetism in the limit of low energies and large systems. It will be a theory that, at the Planck scale, describes a reality so far from everyday experience that its full implications may be beyond our intuitive grasp. Whether such a theory will ever be found, and whether, if found, it can be confirmed experimentally, are questions whose answers lie in the future. But the fact that the question has been asked, the fact that physics has been pursuing the unification of all forces for 150 years, ever since Faraday pointed at the problem, is itself a remarkable testimony to the power of scientific vision. Faraday could not have known, in 1849, the full scope of what he was asking. He could not have known about quantum mechanics, about the nuclear forces, about the Big Bang, about black holes and gravitational waves. He was asking a question that he could not fully understand, about a problem he could not fully see, in a vocabulary that was wholly inadequate to its subject. And yet he asked the right question. The story of Faraday's predictions and their realization, the predictions that came true in the 20th century and the prediction that remains at the beginning of the 21st, still unfulfilled, is a story about the relationship between scientific vision and scientific progress. It is a story about what happens when a mind of extraordinary clarity looks at the physical world and sees, beneath the complexity of appearances, the shape of an underlying order. It is a story about the power of the right question, a question asked without knowing fully what it means or how to answer it, to organize the subsequent development of an entire discipline. It is also a story about patience. Faraday's predictions about electromagnetic technology were not fully realized until half a century after his death. His prediction about the electron required 60 years to confirm. His prediction about the field nature of matter required a century and quantum field theory to vindicate. His final prediction, the unified theory of all forces, has now been pursued for 170 years without reaching its goal. The timescale of fundamental physics is not the timescale of a human life, or even of a generation. It is the timescale of civilizations. Faraday himself understood this, in his quiet, unostentatious way. He was not a man given to grand proclamations or to the self-promotion that characterized many of his contemporaries. He did not seek fame, though fame found him. He did not seek wealth, though he was offered it and declined it. He refused to advise the British government on the manufacture of chemical weapons, and he refused a knighthood on the grounds that he wished to remain plain Michael Faraday to the end. He sought understanding, the specific, patient, experimental understanding of the physical world that his particular genius was suited to achieve. He achieved more of it, in a working life of extraordinary productivity and depth than almost any other scientist in history. He achieved it from a starting point of near total disadvantage. No formal education, no mathematical training, no social connections, no inherited wealth or position. He achieved it through observation, through experiment, through the disciplined exercise of an intuition that could see past the confusing surface of phenomena to the underlying structure beneath. And he left, as the legacy of that achievement, not only the specific discoveries that built the modern world, but the vision of a unified physics. The vision that electromagnetism and light and gravity and the forces of matter were all branches of a single tree that has organized the most ambitious scientific program in human history. The blacksmith's son from Newington Butts looked at a piece of glass between two magnets in the autumn of 1845 and saw, in the rotation of a beam of polarized light, the shape of the 20th century. He saw the radio towers and the power stations and the electric lights. He saw, dimly but unmistakably, the particle accelerators and the quantum fields and the Standard Model. He saw, at the edge of vision, something he could not name. The final unified theory, the theory of everything, the theory that would complete the project that his September experiment had begun. He did not live to see any of it. He died in 1867 at his Grace and Favour House at Hampton Court, which was provided to him by Queen Victoria in recognition of his lifetime of service to British science. He died quietly, without fanfare, surrounded by his wife Sarah and the books and papers that had been his companions for 60 years of intellectual life. He had, in the final years, been plagued by memory loss and fatigue, and had long since retired from active research. But his mind, when it worked clearly, was still the same mind that had seen the unified field in the rotation of a polarized beam of light. He was buried, at his own request, in a simple grave in Highgate Cemetery. His gravestone bears only his name and the dates of his birth and death. He had declined to be buried in Westminster Abbey, in the same ground as Newton and Darwin and the other monuments of British science, on the grounds that he wished for a plain, quiet, private burial. He got what he asked for. What he had given to science, to technology, and to the future, was anything but plain and quiet. It was, arguably, more than any other individual has given to the practical and intellectual life of the modern world. The civilization that we inhabit, the civilization of electric light and wireless communication, of electronic computing and medical imaging, of quantum physics and particle accelerators, is, at its technological foundation, the civilization that Faraday built. Not alone, of course. Maxwell, Hertz, Thomson, Einstein, Bohr, Dirac, Feynman, a long and brilliant succession of scientists built upon what Faraday had laid down. But the foundation was his, the vision was his, the direction was his, and the final prediction, the prediction that all the forces of nature, including gravity, would eventually be understood as aspects of a single underlying unity, remains his. It remains unfulfilled. It remains, in the judgment of the physicists who pursue it, the most important unsolved problem in all of science. It remains the destination toward which fundamental physics has been moving, in fitful steps and false starts, and moments of unexpected illumination, for more than 170 years. When it is finally reached, if it is finally reached, the achievement will be described correctly as one of the supreme intellectual accomplishments in human history. But it will also be, in a sense that is not merely rhetorical, the completion of something that a poor blacksmith's son in a laboratory in Mayfair began on an autumn afternoon in 1845. The questions that Faraday's story raises about the nature of scientific genius are worth exploring in their own right, because they bear on how we understand the relationship between individual human minds and the progress of human knowledge. Faraday was, in almost every respect, an anomaly, a scientist of the very first rank who lacked the formal education and the mathematical training that in his time and in ours are regarded as essential prerequisites for serious scientific work. He never learned calculus. He had no formal training in physics or chemistry, beyond what he absorbed by reading the books that came through Rebau's bindery and attending the lectures of Humphrey Davy. He was, throughout his career, distrustful of pure mathematical reasoning, suspicious of theoretical frameworks that were not grounded in experimental observation, and incapable of the kind of abstract mathematical thinking that characterized the work of Maxwell and later Einstein. His strength lay elsewhere, in the extraordinary acuity of his physical intuition, in his ability to design experiments that isolated and clarified the phenomena he was investigating, in his capacity to see connections between apparently unrelated phenomena that his more mathematically sophisticated contemporaries missed. This combination of strengths, acute physical intuition, experimental mastery, conceptual clarity, gave Faraday a particular kind of scientific vision. A vision that was broad rather than deep in the mathematical sense, that ranged across the entire landscape of physics and chemistry rather than penetrating deeply into any narrow technical domain. He saw the forest, not the individual trees. He saw the pattern, not the detailed structure. And seeing the forest and the pattern is, at certain moments in the history of science, exactly what is needed. The middle decades of the 19th century were such a moment. The individual trees of physics and chemistry were well tended by a generation of highly trained specialists, mathematicians who could handle the calculus of Laplace and Lagrange, chemists who could analyze and classify the compounds of the organic and inorganic world, physicists who could measure and quantify the phenomena of heat and light and sound with impressive precision. What was lacking was the forest, the overall view, the sense of how the different parts of the physical world fit together, the vision of an underlying unity beneath the surface diversity of natural phenomena. Faraday provided that view. He provided it not through mathematical analysis, but through physical intuition, through the ability to see, in a rotating beam of light, the shape of the electromagnetic spectrum, through the ability to see, in the discrete quantities of electricity required to deposit different chemical elements, the existence of the electron, through the ability to see, in the lines of force of a magnet, the structure of a field that pervaded all of space, through the ability to see, in all of these things taken together, the outlines of the unified physics that the next century and a half of research would slowly and painfully construct. The lesson of Faraday's career for the organization of scientific research is not, I think, that we should abandon mathematical training and formal education in favor of untutored intuition. Maxwell's mathematical genius was essential to the translation of Faraday's intuitions into the precise, testable predictions that drove the development of electromagnetic technology. Einstein's mathematical sophistication, his command of Riemannian geometry and tensor calculus, was essential to general relativity. The mathematics of quantum field theory and string theory is far beyond anything that Faraday could have handled. Mathematics is not optional in fundamental physics. The lesson is, rather, that mathematical sophistication is not sufficient, that the ability to handle complex equations, to pursue rigorous arguments through long chains of inference, to work at the frontier of mathematical technique, All of this is necessary, but not enough. That what is also needed at certain moments is the ability to step back from the technical details and see the larger picture, to ask what the equations mean, what physical reality they describe, whether the framework within which they are being applied is the right one, or whether a deeper framework is waiting to be found. Faraday's kind of vision, the vision of the forest, is not teachable in the way that calculus is teachable or experimental technique is teachable. It is something rarer and perhaps irreducible to any set of educational methods or institutional structures. But it can be cultivated, and the institutions of science can create conditions in which it is more or less likely to flourish. The Royal Institution, in Faraday's day, was one such institution, a place where science was conducted in close connection with public engagement, where the Friday evening discourses, which Faraday delivered for many years and which attracted audiences from all levels of educated London society, created a pressure to communicate science clearly and accessibly, without retreating into technical jargon or mathematical abstraction. This pressure, paradoxically, may have helped Faraday maintain the broad, intuitive, cross-disciplinary perspective that was his distinctive strength. The Friday evening discourses and the Christmas lectures, the latter of which Faraday delivered 6 times, most famously the 1848 series on the chemical history of a candle, represented something that was genuinely important about Faraday's conception of science. His belief that the understanding of nature was not the private property of trained specialists, but a common inheritance of humanity, accessible in its essentials to anyone willing to observe carefully and think clearly. He was a passionate advocate for public science education, not merely as a social good, but as an intellectual necessity. He believed that the educated public was not merely a passive audience for science, but a check on the pretensions of specialists. A reminder that scientific theories, however technically elaborate, were ultimately answerable to the ordinary phenomena of the physical world that everyone could observe. This belief, that science was democratic in its ultimate foundations, was radical in the mid-19th century and remains, in some respects, contested today. The technical demands of modern fundamental physics are such that the boundary between what specialists can understand and what educated non-specialists can follow has moved considerably since Faraday's time. String theory cannot be explained to a general audience without a mathematics that most educated people do not have. The Standard Model is accessible to physicists, but opaque to non-specialists in ways that Faraday's electromagnetic field theory never was. The increasing technical specialization of science has created a gap between the scientific community and the wider public that Faraday would have found troubling, and that has genuine consequences for the public's ability to make informed judgments about the role of science in society. But the spirit of Faraday's commitment to public science, the insistence that the fundamental questions science asks are questions that every thoughtful person can understand, even if the technical answers require specialist training, remains as important as ever. The question of whether a unified theory of all forces exists is not a technical question. It is a question about the nature of reality, and it is a question that every human being who has ever looked at the night sky and wondered what holds the universe together has been asking in their own way since the dawn of consciousness. Faraday asked it formally, with the precision of an experimental physicist who had spent his career learning how to extract reliable information from nature about its own structure. He asked it in 1845 and in 1849 and in the years that followed, and he asked it knowing that he would not live to see the answer. He asked it as an act of faith, faith in the unity of nature, faith in the power of human reason to penetrate that unity, faith in the slow but cumulative progress of scientific knowledge toward the truth. That faith has been, in the century and a half since his death, partially justified and partially disappointed. Justified in the sense that the program he initiated has made extraordinary progress. The unification of electromagnetism, the discovery of the nuclear forces and their incorporation into the Standard Model, the unification of the electro-weak and strong forces within the Standard Model's mathematical framework, and the steady accumulation of experimental evidence confirming that the Standard Model is a faithful description of nature up to the energies currently accessible to experiment. Disappointed in the sense that the final unification, the incorporation of gravity into a quantum field theory framework, the completion of the unified physics that Faraday's vision demanded, remains as elusive today as it was when Einstein began pursuing it a century ago. The disappointment, though real, should not obscure the progress. The distance that physics has traveled since Faraday's September experiment in 1845 is almost beyond comprehension. The technologies that his discoveries made possible have transformed every aspect of human life. The theoretical structures that his intuitions inspired have revealed a universe of extraordinary depth and order. The experimental program that his predictions set in motion has confirmed, to a precision that would have seemed miraculous to his contemporaries, that the physical world is governed by mathematical laws of remarkable beauty and unity. The journey that he began has been one of the greatest intellectual achievements in human history. And the journey is not over. The final prediction, the unified theory, still awaits its completion. The physicists who pursue it today are following the direction that Faraday pointed out in a laboratory in Mayfair in the autumn of 1845. They do not, in general, think of themselves as completing Faraday's project. The language of theoretical physics has moved so far from the language of 19th century natural philosophy that the connection is not always obvious. But the connection is real. The question they are asking is the question he asked. The vision that motivates them, the vision of a universe that is, at its deepest level, simple and unified and comprehensible, is the vision he had. Someday, perhaps in a decade, perhaps in a century, perhaps in a millennium, someone will find the answer. They will write down the equations of the theory that unifies all the forces of nature, and they will show how those equations reduce, in appropriate limits, to the standard model and to general relativity. They will have solved the problem that Faraday identified, the problem that Einstein spent 30 years failing to solve, the problem that has occupied the most fertile minds in theoretical physics for more than half a century. When they do, they will be completing something that began not in their own institution or their own century, but in a laboratory on Albemarle Street in London, on a September afternoon in 1845, when a man with no formal education and an intuition of almost supernatural clarity held a piece of glass between two magnets and watched a beam of light rotate. He did not know, on that afternoon, what he had started. He understood it better than almost anyone alive, but he could not have known its full implications. He could not have known about the radio towers and the power stations and the particle accelerators and the string theorists. He could not have known that the rotation of that beam of light would cascade through Maxwell's equations and Hertz's experiments and Marconi's antennas and Edison's generators and Thomson's electron and Rutherford's nucleus and Bohr's quantum and Dirac's equation and Feynman's diagrams and Weinberg's symmetry breaking and Maldaceno's duality into the edifice of modern physics. The most ambitious, the most precise, and the most incomplete intellectual structure that human beings have ever built. He knew only that the beam had rotated, that light and magnetism were connected, that the universe was more unified than it had seemed, and that it was the task of science to find out how much more unified it truly was. He was right, and the task is not yet done. The piece of glass that Faraday used in his September 1845 experiment still exists. It is preserved in the archives of the Royal Institution in London in a small glass-fronted display case, labelled in Faraday's handwriting. It is a dense, slightly greenish piece of lead borosilicate glass, what Faraday called heavy glass, about the size of a large book. It looks, to the untrained eye, entirely unremarkable. There is no visible sign of what passed through it that September afternoon, no mark or trace left by the beam of polarized light and the magnetic field that bent it. But look carefully at the label. Faraday's handwriting was small and precise, the handwriting of a man who kept meticulous records and believed that the integrity of scientific observation depended on the accuracy of its documentation. The label reads, "Glass from experiment 9th of September 1845, and beneath that, in the same small, precise hand, basis of all subsequent researches. He was right about that too. Every subsequent research, the whole 20th century and more, the edifice of modern physics and modern technology, all of it had its foundation in what happened to the light that passed through that piece of glass. And somewhere, in a laboratory, or a theoretical physics department, or a quiet office, late at night, the work continues. The equations accumulate. The ideas are tested and found wanting, and revised and tested again. The answer, when it comes, will not look like anything Faraday could have imagined. It will be written in a mathematical language that did not exist in his time and will require a conceptual framework that does not yet exist in ours. But it will be, at its heart, the answer to Faraday's question. The question he asked on the 9th of September, 1845, in the most important sentence he ever wrote in his laboratory notebook, that there is some connection between these two great agents of nature, electricity and gravity, I cannot doubt. He could not doubt it. He was right not to doubt it. And the physics of the coming centuries will prove him right in full. When it finds, at last, the unified field that he saw, imperfectly but unmistakably, through the rotation of a beam of light. To understand the full scope of what Faraday predicted, it is worth pausing on the specific details of his experimental life and the particular intellectual moves that led from one discovery to the next. Because Faraday's predictions were not armchair speculations. They were grounded, every one of them, in specific experimental observations that he had made and that he understood more deeply than anyone else alive. Consider the sequence of experiments that led to his September 1845 discovery. Faraday had been trying to demonstrate a connection between light and electromagnetism for years before he succeeded. His laboratory notebooks from the early 1840s contain repeated accounts of failed experiments. Attempts to detect a change in the properties of a beam of light when it passed through an electrically charged medium. Attempts to detect a rotation of polarized light in the vicinity of current-carrying wires. Attempts to show that a magnetic field could affect the propagation of light in transparent materials. The failures were systematic and instructive. They told him not that the effect did not exist, but that his apparatus was not sensitive enough to detect it, or that he was looking in the wrong place. The insight that eventually led to success was a change in the medium. Earlier experiments had used gases or simple liquids. In September 1845, Faraday used a piece of heavy glass, a dense lead-containing glass of his own manufacture, which had much higher optical density than ordinary glass and was therefore much more sensitive to the magneto-optical effect he was seeking. The choice of this particular material was not obvious. It required Faraday to combine his knowledge of optical materials, developed in his early chemistry work, with his physical intuition about where the effect was most likely to be found. It was a characteristic Faraday move, the right experiment, with the right material, designed by someone who understood the physics well enough to know where to look. The discovery of the magneto-optical effect in September 1845 was followed, within weeks, by another major discovery, diamagnetism. Faraday discovered that materials which were not magnetic in the ordinary sense, wood, glass, water, bismuth, were actually slightly repelled by a magnetic field, rather than being attracted to it or unaffected by it. This was a completely unexpected result. The conventional wisdom of the time divided materials into magnetic, attracted to magnets, and non-magnetic, unaffected by magnets. Faraday showed that the conventional wisdom was wrong. All materials responded to magnetic fields, but most responded so weakly and with a repulsion rather than an attraction that the effect had never previously been noticed. The discovery of diamagnetism was, in one sense, a relatively minor result, an interesting oddity of magnetic behavior that extended the known phenomenology of magnetism without fundamentally changing the theoretical picture. In another sense, it was the first confirmation of a prediction that Faraday had made on the basis of his field theory. If magnetic fields were real physical entities that pervaded all of space, then all matter, not just iron and a few other magnetic materials, must interact with them. The discovery of diamagnetism confirmed this prediction. Every material interacted with magnetic fields. The universe was, as Faraday had said, full of fields, and those fields acted on everything. This theme, the universality of fields, the idea that the electromagnetic field was not a local phenomenon, but a structure that permeated all of space, ran through everything that Faraday did in the 1840s and 1850s, and it is the theme that connects his experimental discoveries to his theoretical predictions. The field was everywhere. It acted on everything. It was the medium of all electromagnetic and optical phenomena, and it was, Faraday believed, connected to gravity. Connected to the force that alone among the known forces of nature, he had not succeeded in demonstrating a connection to the electromagnetic field. He tried repeatedly to detect a connection between gravity and electromagnetism. He dropped magnets through conducting tubes and measured the induced current, looking for a deviation from the prediction of simple electromagnetic induction that might indicate a gravitational contribution. He measured the electrical properties of materials at different heights above the Earth's surface, looking for a correlation with the local gravitational field. He suspended electrically charged bodies and looked for gravitational effects on the electric field around them. All these experiments gave negative results, as they had to, since the connection between gravity and electromagnetism, if it exists, operates at energy scales so far below the sensitivity of 19th century equipment that no experiment Faraday could have performed had any chance of detecting it. He knew this. He wrote in his experimental notebook that the negative results of his gravity-electricity experiments did not discourage him, because he was confident that the sensitivity of the experiments was far too low to detect an effect that might still exist. He was, in this assessment, exactly right. The ratio of the electromagnetic force to the gravitational force between two electrons is approximately 10 to the power of 42, a 1 followed by 42 zeros. The gravitational force between two elementary particles is so much weaker than the electromagnetic force that the most sensitive experiments of the 19th century, or indeed of the 20th century, could not have detected it directly. Faraday's failure to find a gravitational electromagnetic connection experimentally was not a failure of imagination or experimental skill. It was a consequence of the extreme weakness of the gravitational force at the microscopic scale, a weakness that is itself one of the great mysteries of fundamental physics. The hierarchy problem, the question of why gravity is so much weaker than the other fundamental forces, is one of the central unresolved puzzles of the Standard Model. The electromagnetic, weak, and strong forces have strengths that are within a few orders of magnitude of each other at the energies accessible to current accelerators. Gravity is 40 orders of magnitude weaker. No satisfactory explanation for this extraordinary disparity in the strengths of the fundamental forces has been found within the Standard Model. Various theoretical ideas, supersymmetry, extra dimensions, and the anthropic principle have been proposed as explanations, but none has yet been confirmed experimentally. The hierarchy problem is deeply connected to the quantum gravity problem. If gravity were not so much weaker than the other forces, the Planck scale, the energy at which quantum effects in gravity become important, would not be so far above the energies accessible to current experiments. If the Planck scale were closer to the scales currently probed by particle accelerators, the physics of quantum gravity would be experimentally accessible, and the problem of unifying gravity with quantum mechanics would have been solved long ago. The extreme weakness of gravity, the fact that a pocket magnet can lift a paperclip against the gravitational pull of the entire Earth, is, in a sense, the reason why Faraday's final prediction has not yet been confirmed. Yet even in this, there is a kind of vindication of Faraday's vision. The hierarchy problem, the question of why the forces have such different strengths, is, at a deeper level, a question about the structure of the unified theory that Faraday predicted. If all the forces are aspects of a single underlying reality, then their apparent differences in strength must be explained by the way in which that underlying reality manifests at the energy scales accessible to our experiments. The hierarchy problem is not a problem that arises if you assume that gravity and electromagnetism are truly independent forces with no deeper connection. It is a problem that arises precisely because you believe, as Faraday did, that they are connected, that their apparent differences must be explained by the structure of the deeper theory that unifies them. In this sense, the outstanding problems of fundamental physics, the hierarchy problem, the quantum gravity problem, the nature of dark matter and dark energy, the origin of the matter, antimatter asymmetry, are all, at some level, problems that follow from taking Faraday's prediction seriously. They are the problems you have when you believe that the universe is unified and attempt to understand how the unified reality gives rise to the apparently diverse phenomena that we observe. They are the problems of the research program that Faraday initiated. The history of that program in the 20th century is also the history of several remarkable predictions that were made and confirmed. Predictions that trace a direct line from Faraday's works to the physics of today. The most dramatic of these was the prediction of antimatter. In 1928, Paul Dirac, a theoretical physicist at Cambridge of almost supernatural mathematical ability, combined the equations of quantum mechanics with the requirements of special relativity to produce what is now called the Dirac equation, the relativistic equation governing the behavior of the electron. The Dirac equation had a troubling property. It admitted solutions with negative energy. In classical physics, negative energy solutions could be dismissed as unphysical. In quantum mechanics, they could not. The mathematics of quantum mechanics required that all solutions be taken seriously. Dirac initially tried to interpret the negative energy solutions as protons, the only other charged particle known at the time. This did not work. The mathematics showed that the negative energy partners of electrons had to have the same mass as electrons, whereas protons are nearly 2,000 times heavier. In 1931, Dirac proposed the correct interpretation. The negative energy solutions described a new kind of particle, a positively charged electron, an anti-electron, with the same mass as the electron, but opposite charge. He predicted that if an electron and an anti-electron met, they would annihilate, converting all of their mass into electromagnetic radiation. He predicted that pairs of electrons and anti-electrons could be created from electromagnetic radiation if the radiation had sufficient energy. This was an extraordinary prediction. No antiparticle had ever been observed. The concept of antimatter, of particles that were mirror images of ordinary particles in terms of their charge, was entirely new, and yet Dirac's prediction followed inevitably from the mathematics of his equation. If you combined quantum mechanics with special relativity, antimatter was not optional. It was required. In 1932, Carl Anderson at Caltech, examining cosmic ray tracks in a cloud chamber, observed a particle with the same mass as the electron but opposite charge, the positron, or anti-electron, that Dirac had predicted. It was the first antiparticle ever detected, and it confirmed Dirac's prediction with a completeness that silenced all doubters. Antimatter was real. The connection to Faraday is not immediately obvious, but it is real. Dirac's equation was, in its mathematical structure, a direct descendant of Maxwell's equations. The requirement of relativistic invariance that drove Dirac to his equation was a requirement that arose from Maxwell's electromagnetism and Einstein's special relativity. The field-theoretic framework within which Dirac worked, the framework in which the electron was described as an excitation of a quantum field rather than a classical particle, was the framework that Faraday had initiated with his concept of the electromagnetic field and Maxwell had formalized. The prediction of antimatter was a prediction that could only have been made within this framework. It was, in a deep sense, a further consequence of Faraday's insight that nature was best described in terms of fields rather than particles. The subsequent history of quantum field theory, QED in the 1940s, the electroweak theory in the 1960s, QCD in the 1970s, continued this tradition. Each new quantum field theory extended the framework that Faraday had initiated. Each new particle predicted by these theories was confirmed experimentally. The W and Z bosons, predicted by the electroweak theory in 1967 and discovered at CERN in 1983, were perhaps the most dramatic of these confirmations. Massive particles whose masses were calculated, from the electroweak theory, to be about 80 and 90 times the proton mass, and which were found when the appropriate accelerator energy was achieved at exactly those masses. The prediction and confirmation of the W and Z bosons was one of the greatest triumphs of theoretical physics in the 20th century, and it was a triumph that lay at the end of a chain of reasoning that began with Faraday's field concept. The Higgs boson, predicted by Peter Higgs and others in 1964 and discovered at CERN in 2012, extended this chain further. The Higgs mechanism, the process by which the W and Z bosons acquire their mass, required the existence of a new quantum field, the Higgs field, permeating all of space. The Higgs boson was the excitation of this field, just as the photon was the excitation of the electromagnetic field. Its discovery was not only a triumph for the Standard Model, but a further confirmation of the field-theoretic picture of nature that Faraday had pioneered. The universe was, as Faraday had said, full of fields. Another field had been found. The confirmation of the Higgs boson also raised new questions, because the properties of the Higgs field, its mass, the strength of its interactions with other fields, the way in which it interacts with gravity, are among the quantities that a unified theory of all forces ought to predict, but that the Standard Model simply takes as inputs. The Higgs mass is one of the quantities most afflicted by the hierarchy problem. Quantum corrections to the Higgs mass, calculated within the framework of the Standard Model, are enormously larger than the observed value, requiring a precise cancellation of large contributions that seems, from the perspective of the Standard Model, entirely accidental. This accidental cancellation, which physicists call fine-tuning, is one of the strongest indications that the Standard Model is an incomplete theory, that something lies beyond it. What lies beyond the Standard Model? What the deeper theory is that explains the Higgs mass without fine-tuning, that incorporates gravity, that explains dark matter and dark energy, is the central question of contemporary fundamental physics. It is the question that the Large Hadron Collider was built to answer, at least in part, and the LHC's discovery of the Higgs boson, combined with its failure to discover anything else beyond the Standard Model, has put the field in a position of uncomfortable uncertainty. The theory works, but it seems to work in a way that cries out for a deeper explanation, and the deeper explanation has not yet been found. The discomfort of this situation is palpable in the theoretical physics community. A generation of physicists was trained in the 1980s and 1990s to expect that the LHC would discover supersymmetric particles, the supersymmetric partners of the Standard Model particles predicted by the most popular extension of the Standard Model. Supersymmetry, which postulates a symmetry between matter particles, fermions, and force-carrying particles, bosons, was expected not only on theoretical grounds, it elegantly solved the hierarchy problem, but because it was required by the simplest versions of string theory. The LHC has found no evidence of supersymmetry. This does not mean that supersymmetry is wrong. The supersymmetric particles might exist at masses just beyond the current reach of the LHC, but it has substantially weakened the theoretical case for the simplest versions of supersymmetric theories. The current situation in fundamental physics has some features in common with the situation that existed at the end of the 19th century, when physics appeared to many of its practitioners to be essentially complete. When the great classical theories of mechanics, thermodynamics, and electromagnetism seemed to provide a comprehensive framework for understanding all physical phenomena, and the task of physics appeared to be one of increasingly precise measurement rather than fundamental theoretical innovation. The two clouds on the horizon, the null result of the Michelson-Morley experiment, seeking the ether, and the ultraviolet catastrophe in blackbody radiation, turned out to presage the two revolutions of the early 20th century, special relativity and quantum mechanics. Today's physics has its own clouds: the hierarchy problem, the quantum gravity problem, the nature of dark matter and dark energy, The origin of the matter, antimatter asymmetry. Whether these clouds presage a similarly radical theoretical revolution, a revolution that will make the current standard model seem as incomplete as Newtonian mechanics seemed after Einstein, or whether the resolution will come through more conservative extensions of existing frameworks, is impossible to say. The history of physics suggests that when apparent anomalies persist long enough and accumulate sufficient weight, a revolution eventually comes. But history does not specify the timeline. Faraday's own relationship to the revolutions of physics is instructive in this context. He worked at a time, the mid-19th century, when Newtonian mechanics seemed unshakably correct, and the task of physics was to apply it to new domains. His discoveries, the electromagnetic field, electromagnetic induction, the laws of electrolysis, extended the domain of physics without initially challenging its Newtonian framework. But the implications of his discoveries, fully worked out by Maxwell and then by Einstein, ultimately required a radical revision of the Newtonian framework. The abandonment of absolute time and space, the introduction of the field as a fundamental physical entity, the replacement of action at a distance with the local propagation of field influences. Faraday did not live to see these revolutions. He did not anticipate them in their details. But his discoveries set them in motion. The current generation of physicists may be in a similar position, making discoveries and developing theories whose full implications will only be worked out by succeeding generations. The ADES-CFT correspondence, the ER-EPR proposal, the connections between quantum gravity and quantum information, all of these may be the Faraday equivalent contributions of our era. Not the final answer, but the observations and intuitions that will eventually lead, through the work of mathematical successors, to the final answer. If so, the prediction that Faraday made in 1849, that gravity and electricity, and by extension all the forces of nature, are connected, will be confirmed not in a single dramatic experiment, but in the slow accumulation of theoretical insight and experimental evidence that characterizes the actual practice of science. Not in a September afternoon, but across centuries. The story of Michael Faraday is, in the end, a story about time. About the time it takes for a scientific vision to be fully realized, about the patience required to pursue a problem that will not be solved in a single lifetime or a single generation, about the way in which individual human lives, each bounded and finite, contribute to a collective intellectual project that is bounded by nothing, that extends, in principle, as far into the future as human civilization itself. Faraday understood this. He expressed it in his characteristically plain and undramatic way in his response to the question about the use of a newborn child. The question, in the most fundamental sense, was unanswerable. The use of a newborn child could not be foreseen from the moment of birth. The child might grow up to be anything: a blacksmith, a philosopher, a scientist, a poet. The child might, as Faraday himself had done, transform the world. The child might do nothing of note, or might do something whose note would not be recognized for centuries. You could not know in advance. You could only nurture and wait. Scientific discoveries are like that. Faraday's September experiment was a newborn child, small, apparently unremarkable, attended by a handful of colleagues in a laboratory that most of London did not know existed, born into a world that had no vocabulary for what it would grow up to become. The radio towers and the power stations and the particle accelerators and the string theorists, none of them were visible from the moment of birth. The experiment had to be nurtured by Maxwell and Hertz and Einstein and Thomson and Dirac and all the others across decades and generations before it could become what it has become. The foundation of the most technically sophisticated civilization in human history and the origin of the most ambitious and most incomplete scientific program in the history of human thought. Faraday nurtured it for the 22 years between the September experiment and his death in 1867. In that time, he continued to publish, to think, to speculate, to experiment where his health and his failing memory permitted. He continued to give the Friday evening discourses and the Christmas lectures. He continued to correspond with Maxwell, encouraging the young mathematician's work on electromagnetic theory with the generosity that was one of his most characteristic traits. He continued to attend services at the Sandemanian church, finding in the worship of the community he had belonged to since childhood a sustenance that his scientific work, however deeply he loved it, could not provide alone. He was by all accounts a man at peace with himself and with the world, not because he had no uncertainties or disappointments, but because his inner life was organized around commitments that went deeper than scientific success or professional recognition. He cared about truth, about experimental honesty, about the integrity of the scientific record. He cared about his wife, Sarah, to whom he was devoted throughout their 59 years of marriage, and whom he described, in a letter written near the end of his life, as a pillar above all earthly help. He cared about the Sandemanian community, whose rituals and commitments and shared life gave him a sense of belonging that the scientific world, however welcoming it had been to him, could never quite replicate. He was, in the old-fashioned sense of the word, a good man. Not perfect, he had his vanities and his occasional blind spots, his moments of impatience and his tendency to hold on to ideas that the evidence should have led him to revise. But he was, in his fundamental orientation, a man of exceptional integrity and exceptional generosity, who happened also to be a scientist of genius. The combination is rare enough that when it occurs, it creates something that is more than the sum of its parts. A scientific life that is also a human life in the fullest sense, lived with complete commitment to both truth and goodness, and leaving behind not only a body of knowledge, but an example. The example is part of the legacy. The discoveries are part of the legacy. The predictions are part of the legacy. And the final prediction, the one that hasn't yet been fulfilled, is, in its way, the most important part of the legacy of all. Because a prediction that remains unfulfilled is not a failure. It is a direction. It is a finger pointing toward the horizon, saying, "That way. There is something there. We don't know exactly what it is, and we don't know exactly how to get there, but it is there, and we should go." The fact that we have been going in that direction for 170 years and have not yet arrived is not a cause for despair. It is a cause for the particular kind of exhilaration that comes from pursuing a problem that is large enough, deep enough, and important enough to be worth the pursuit, even when the destination is still beyond the horizon. Faraday would have understood that exhilaration. He would have recognized it as the feeling he had on that September afternoon in 1845, when the beam of polarized light rotated, and he understood, in an instant of extraordinary clarity, that the universe was more unified than he had known. The rotation of the beam was small, barely measurable with the instruments of his day, but it pointed toward something immeasurably large. It pointed toward the full electromagnetic spectrum. It pointed toward quantum field theory and the Standard Model. It pointed, at the very edge of vision, toward the unified theory of all forces that remains. To this day, the greatest outstanding problem in the history of science. He saw it all in that small rotation of a beam of light. He couldn't have described what he saw in the language that physics now uses. He didn't have the words. He had only the intuition and the honesty to trust it, and the patience to know that the words would come. If not in his lifetime, then in some other lifetime. If not in his century, then in some other century. The words are coming, slowly, in the long grammar of scientific understanding that takes centuries to form a single complete sentence. But they are coming, and when they finally arrive, when the unified theory is written down and confirmed and understood, they will be, in the deepest sense, Faraday's words. The September experiment, the rotating beam, the beginning of everything. There is one more dimension of Faraday's story that deserves attention before we leave it, the dimension of place. The Royal Institution of Great Britain, the institution where Faraday worked for the entirety of his productive scientific life, is still standing at 21 Albemarle Street in Mayfair, London. It is one of the oldest scientific institutions in the world, founded in 1799, and it is one of the most remarkable buildings in the city, a plain Ionic facade that gives no hint of the extraordinary intellectual history within. The laboratory in which Faraday made his discoveries, including the September 1845 magneto-optical experiment, has been preserved and can be visited today, restored to something like its 19th century appearance. The wooden benches on which his apparatus stood, the gaslights that illuminated his experiments, the heavy electromagnetic apparatus with its hand-wound coils and its primitive measuring instruments. All of it has been preserved with a care that reflects the understanding that this place is, in the history of science, sacred ground. Not sacred in any religious sense, though Faraday himself would not have drawn that distinction sharply. Sacred in the sense that matters in secular modernity, a place where something happened that changed the world. The Royal Institution was also the site of the Friday evening discourses and the Christmas lectures that Faraday used to communicate his science to the public. The lecture theatre where he stood, a small, steeply raked amphitheatre with seating for around 400 people, unchanged since Faraday's day, is still used for lectures today. The Christmas lectures, which Faraday delivered 6 times between 1827 and 1860, still take place at the Royal Institution every December and are still broadcast to a mass television audience. The tradition that Faraday began of making the most exciting and important science of the day accessible to a general audience, including, above all, to children, has outlived him by more than a century and a half. This is not a coincidence. Faraday believed, with the same certainty, that he brought to his scientific work, that public engagement with science was not a luxury, but a necessity, not merely a social good, but an intellectual and democratic imperative. He believed that science, conducted in public institutions with public funding for the public benefit, owed the public not just the results of its work, but the understanding of how those results were obtained and why they mattered. He believed that a public that understood science was not merely better equipped to make democratic decisions about policy and technology, but was itself enriched, made more fully alive to the world they inhabited, more deeply aware of the extraordinary complexity and beauty of the natural order. This belief was not naive. Faraday was not suggesting that everyone could or should understand the mathematical details of electromagnetic theory. He was suggesting something more fundamental, that the experience of discovery, the moment of seeing that something you had previously thought was separate was actually connected, the moment of recognizing pattern and order beneath apparent complexity, was an experience available to every human being, regardless of mathematical training, and that the role of science communication was to recreate that experience for audiences who had not made the technical journey themselves. His Christmas lectures on the chemical history of a candle are perhaps the most successful realization of this ambition in the history of science communication. In 6 lectures delivered to a mixed audience of young people and adults in December 1848 and January 1849, Faraday used a candle as a window into the whole of chemistry and physics. Starting from the simplest observations about a burning flame, its shape, its color, its consumption of wax and production of heat, he moved, step by step, into the chemistry of combustion, the physics of convection, the composition of the atmosphere, the nature of carbon and hydrogen and oxygen, the structure of matter, the principles of heat and light. The lectures were documented and published, and have been in print continuously ever since. Richard Feynman, the physicist who, more than any 20th century figure, inherited Faraday's mantle as both a physicist of genius and a communicator of extraordinary skill. Read them as a young man and describe them as among the most influential books in his intellectual development. The Candle Lectures are, in miniature, what Faraday's entire scientific career was in full. The demonstration that a single, simple, familiar phenomenon, examined with sufficient care and curiosity, opens a window onto the entire structure of the physical world. The candle was a window onto chemistry and physics. The September 1845 experiment was a window onto the unified field. Faraday's genius was the same in both cases, the ability to see, in the particular, the universal, to look at one thing and perceive, through it, everything. This is the quality that makes his story so enduring, so capable of speaking across the century and a half that separates us from him. We live in a world shaped more thoroughly by his discoveries than by those of almost any other individual in history. We use, every day, technologies that exist because of what he found in his laboratory. The electric light, the electric motor, the generator, the radio, the television, the mobile phone. We live in a civilization whose energy infrastructure, the grid of power stations and transmission lines and distribution networks that keeps our lights on and our machines running, is built on the principle of electromagnetic induction that he discovered in 1831. We communicate through a global network of electromagnetic signals, radio waves, microwaves, light pulses in optical fibers, that Maxwell's equations describe with perfect precision, and that would not exist without Faraday's September 1845 experiment. And we live in a scientific culture that is engaged still in the project that he initiated, the project of finding the unified theory of all forces, the single mathematical framework that will describe everything. That project has not been completed. It may not be completed in our lifetimes, but it is being pursued with a seriousness and an intensity that Faraday would have recognized and approved by thousands of theoretical physicists working in institutions around the world. They are following the direction he pointed. They have not yet arrived where he directed them to look. They will. Eventually, they will. The history of physics is a history of eventually, of problems that seemed impossibly hard until they were solved, of unifications that seemed impossibly ambitious until they were achieved, of predictions that seemed impossibly bold until they were confirmed. Every major advance in physics has been made by people who believed, against the evidence immediately available to them, that the universe was more unified and more comprehensible than it appeared. Faraday believed this. Maxwell believed it. Einstein believed it. The current generation of physicists who are pursuing quantum gravity and the unified theory believe it. They are right to believe it. The evidence, accumulated over 170 years of extraordinary effort, points unmistakably in that direction. The universe is unified. The forces are connected. The final theory exists. It has not yet been found, but it exists, waiting to be discovered by the mind that is capable of seeing it. The mind that will look at some equation or some experimental result and to understand, as Faraday understood when the beam rotated, that something previously thought to be separate is actually connected, that the world is, at its deepest level, one. That is Michael Faraday's prediction. That is Michael Faraday's legacy. And that is the story that began on the 19th of September, 1845, in a laboratory on Albemarle Street in London, when a blacksmith's son held a piece of glass between two magnets and watched a beam of light rotate, and saw, in that small rotation, the shape of everything. There is a question that inevitably arises when one considers Faraday's life and his predictions. What would he make of the world that his discoveries created? This is not, of course, a question that can be answered, but it is a question worth asking, because the act of imagining Faraday in the present illuminates something important about both him and us. He would, almost certainly, have been astonished by the technological transformation of the physical environment. A man who had grown up by candlelight and worked by gaslight would find the electric illumination of a modern city. The streams of headlights on motorways, the glowing grids of office windows, the pulsing blue light of mobile phone screens, almost incomprehensible in its scale, though entirely comprehensible in its underlying physics. He would recognize, in every electric light and every wireless communication device, the working out of principles that he had discovered. He would find it gratifying, I think, that the physics was right. He might find it overwhelming that it had been applied so completely, so universally, on such a planetary scale. He would also, I think, have been deeply uncomfortable with aspects of the world his discoveries made possible. He had refused to advise the British government on the development of chemical weapons during his lifetime, on grounds of personal conscience. The use of his discoveries, of the electromagnetic radiation, of the electric power grid, in the machinery of 20th century warfare would have troubled him. The radar systems that guided bombers over German cities, the communication systems that coordinated military operations, the electromagnetic pulse weapons that could disable entire power grids. All of these were applications of physics that Faraday had done, turned to purposes that he would have found abhorrent. He was not naive about the relationship between science and power. He lived at a time when British science was deeply entangled with British imperial ambition, and he was not unaware of that entanglement. But he maintained, throughout his life, a personal separation between his scientific work and the political and military uses to which it might be put. He saw his work as a contribution to human understanding, not to human destructive capacity. The fact that human understanding could be, and repeatedly was, turned to destructive purposes was a fact about human nature that science could not change. He would, I think, have found more consolation in the medical applications of his discoveries. The electric power systems that run hospital equipment, the electromagnetic radiation used in MRI scanners and radiotherapy, the electronic monitoring systems that track patients in intensive care, all of these are applications of physics that Faraday initiated, turned to the purpose of preserving and extending human life. He would have recognized, in these applications, something closer to what he had hoped his work might achieve: the improvement of the material conditions of human existence, the reduction of suffering, the extension of the scope of human possibility. He would, above all, have been fascinated by the state of fundamental physics. The standard model, the quantum field theory of the electromagnetic weak and strong forces, would have been, to him, an extraordinary vindication of his intuition that all the forces of nature were expressions of a single underlying reality. The confirmation of the Higgs boson would have seemed to him like the discovery of one more field pervading all of space, one more confirmation of the picture of the physical universe as a vast, self-interacting field structure, which was the picture that his experimental discoveries had first suggested. And the unsolved problem of quantum gravity, the failure, after 60 years of effort by the most brilliant theoretical physicists alive, to incorporate gravity into the quantum field theory framework, would have seemed to him familiar, recognizable, almost consoling, not because he would have been pleased that the problem was unsolved, but because the fact that the problem remained would have confirmed his intuition that it was hard. He had suspected, in his later years, that the unification of gravity and electromagnetism was a problem that would not yield easily. He had failed, repeatedly, to find experimental evidence for it. He had known that the problem required something beyond what physics possessed in his time. He would have been reassured, I think, to find that physics now possesses vastly more than it did in his time, and that the problem, though still unsolved, is understood far more precisely. He would have been reassured that the direction in which he pointed, the direction of unification, of the field, of the underlying simplicity beneath the apparent complexity of natural phenomena, has proved, at every step, to be the right direction. And he would have understood, from his own experience of problems that took years of failed experiments before yielding, that the right direction and the easy direction are not the same thing. He was patient, he was persistent. He was humble about what he did not know, and rigorous about what he did. These are the virtues that the problem of quantum gravity demands, and they are the virtues that the scientific community engaged in. That problem is, at its best, exercising. The final prediction has not yet been confirmed, but the virtues are in place, the direction is right, and the universe, which is, after all, what Faraday spent his life studying, is not going anywhere. The September experiment, the rotating beam, the beginning of everything that came after, and the pointer toward everything that is still to come. Michael Faraday, 1791 to 1867. The greatest experimental physicist in British history, and the man who predicted the 20th century from the vantage point of a laboratory bench in 1845. His final prediction still awaits its confirmation. When it comes, it will be, in the most literal and the most profound sense, the end of a story that he began. We are living in the middle of that story. That, perhaps, is the most remarkable thing of all.